Up next is the Boolean workflow. In this chapter, I will explain the Boolean modeling workflow, its uses, pros and cons, and how to identify machine shapes in weapons. Booleans allow for the creation of very complex shapes through the addition, subtraction, or intersection of simpler overlapping shapes. The addition operation will take both objects and try to fuse them together where they intersect, essentially adding the volumes together into a single object. The subtraction operation means that we take one object and cut out the volume that it shares with another object, essentially carving into it based on the shape of the first object. The intersect operation will take the two objects and keep only the volume that they both occupy, removing everything else. Modeling each Boolean shape, it's relatively easy, but combined, we can achieve very visually interesting results. The order in which we execute these operations matters. If we first do an addition and then a subtraction, the subtraction will also affect the added volume from the first operation. Booleans are as old as 3D modeling itself, and have been used destructively in many traditional workflows. An example could be a round shape, like a cylinder, subtracted to a cube, then the mesh is collapsed and the geometry is cleaned up and made ready for subdivision in any desired method, sub-D, bevels, face width and normals, etc. But the Booleans with the most time-saving potential, though, are live Booleans, which exist as separate uncollapsed objects and allow us infinite non-destructive modeling. These are the defining quality of CAD programs like Fusion or Moi, but we can also use them in traditional polymodeling tools like Blender, Max, or Maya, or in more advanced software like 2.5D-based ZBrush or Voxel-based 3D Code. By doing most of our modeling as live Booleans, revisions usually only affect a few operands and don't require a complete remodeling of the whole mesh. With live Booleans at the first stage of modeling, base mesh to high poly, it's better to keep the geometry of the operands extremely dense, using very high segment counts in curved surfaces. This will make the remeshing and smoothing steps produce better, less steppy results. Working with complex surfaces, it's good to check that they will subdivide correctly every now and then. Later, when we generate the low poly geometry, we can dial this density back into an acceptable low poly count operand by operand, again without a big retopology needed, because all the Booleans are live and independent. As pros of live Boolean modeling, we have: they are non-destructive. Live Booleans give us the possibility to easily change any shape at any moment without disturbing the whole. They increase modeling speed. We don't need to care about the ramifications of what we are modeling at any time. It results in speed and peace of mind. They are great for matching complex real-life shapes, where modeling requires lots of small changes that could potentially disrupt the entire geometry if done in the wrong order. Simpler operands are much easier to understand. This is akin to breaking down a big task into smaller, more manageable chunks. A big task might seem daunting when seen all combined, but if we divide it and go piece by piece, it suddenly becomes just a series of small, easy tasks. The remesh and smooth pipeline works on any geometry. This is kind of a silver bullet of modeling. Taking topology out of the equation means we can safely use this method on any weird geometry we want. The more complex the object, the more time we'll likely save by using it. Then again, they also have some cons. They are not suitable for all shapes, or rather, all shapes are suitable, but it's not efficient nor clever to force Booleans into literally everything, like organic stuff. They require strict organization. Keeping everything live is great, until there's so much stuff we can't find where things are. Too many Booleans become hard to keep track of, so it's essential to keep everything properly named, grouped, and parented. They are computationally more complex than regular modeling. This more advanced method is also more prone to technical errors, especially live Booleans that interact with many others at the same time can become finicky when joining questionable geometry together unless done in a certain order. The low poly mesh requires cleanup. Dirty geometry from Boolean operations makes a cleanup step inevitable, although cleaning up the low poly is nothing in comparison to the time saved creating the high poly. Booleans are great for complex hard surface pieces, and especially good for machine shapes, whose internal shape logic we can analyze, dissect, and then nail. These shapes also tend to have very consistent edge bevels, which carries perfectly into the remesh and smooth workflow that will result in uniform edge smoothing. In this regard, firearms are the prime example of assets that are perfect for this workflow. Because of the nature of how they work, passing cartridges through their mechanism and then ejecting them, their shapes are usually complex and interconnected. Assets with more of a thin surface, like a car body or blade weapon, are not ideal in this workflow. They are normally easier to control with a traditional sub-D pipeline. Despite this, they might benefit from Booleans if they have connection points to other, more mechanical shapes. Booleans are also great when we want to decouple or constrain a part of a shape from the main modeling body. These constraints inform us about how far we can stretch certain shapes. For example, we have the magazine of a pistol. Once we have its size, we can Boolean it into the pistol's body, and we will get an idea of how thick we can make it to make the magazine fit inside. Another example are antique rifles with wooden parts. These are easy to model in sub-D in one piece, but then we can constrain certain shapes that would be sawn off during its IRL manufacturing process, and at the same time make modeling easier for us. The cut at the end of the stock or the cuts around the rear sight are examples of this Boolean use. This way, we don't have to worry about cleaning up the geometry each time we modify the main shape, which can change quite a lot since wooden rifle shapes are difficult to understand and match. To break down complex shapes, we will need to follow their hierarchy of importance, going from the general to the particular. The rule of thumb is we focus first on the biggest shapes, the ones that affect big chunks of the main object and its silhouette, and then work our way down until we get to the smallest surface details, like serrations, grooves, or small holes. That said, if we get stuck trying to figure out a bigger shape, it's good to change focus and try to solve other, smaller booleans in the meantime. Maybe some secondary shapes can help us understand the main one. Since all operands are live, we can go back to any one of them and edit them, so there's no real downside to this. We can also take a small break. Sometimes we just need some fresh and well-rested eyes to figure out a difficult shape. In this image sequence, we can see the modeling progression of a pistol slide. First, the bigger shapes from barrel, chamber, and rails. Then, the serrations and the front and rear side mounts. And finally, superficial details like the pin and screw holes. Making models out of booleans becomes even easier when we recognize shape patterns that we can easily replicate using modifiers. The first of these patterns are linear arrays, which come from the linear repetition of a single shape, usually subtracted to the main body of the weapon. Most of these are symmetrical, so that's one thing we can get out of the way easily by using a mirror modifier. Common cases of these are serrations on pistol slides, grooves on pistol grips to make them less slippery, and ventilation holes in barrel covers and muzzle brakes like the ones on the Barrett sniper rifle. The second type of pattern are radial arrays, whose shapes follow a circle instead of a line. They are a bit more tricky to configure than linear arrays, and we can find them in cylindrical weapon parts. The most prominent examples of these are grooves and notches in the revolver cylinders and ratchets, vents in cylindrical barrels, and sniper scopes. The third and final pattern we'll see today are instance shapes, most notably screw holes present in polymer-based weapons to join both sides of the body. We can instance these booleans to keep a consistent size between them, since they are standardized in real life. This way we can avoid having to correct each shape later, once we make the screw that fits in it. After the booleans are done, how much should we smooth them? One of the aspects that contributes to the realism of our weapons is the accuracy of small details, down to the very edge sharpness of each piece. For this reason, we should study or at least be aware of how different pieces are made. A good amount of detailed references is paramount for this. The material and manufacturing process affect the final look of every piece and their edges, and we should take both into consideration when modeling to visually separate different pieces from the high poly to the final in-game mesh. Of course, our target being a video game real-time rendering, poly count, pixel, and texture resolution are limiting factors. We will still need to exaggerate the size of our sharpest edges a little bit so the bake holds up better over distance. In this regard, consistency within our mesh is more important than pure realism. We're making video game weapons, so them working well on screen is our primary concern. We must also be aware of how the gun's pieces are assembled, so we can join them in the same way in 3D, even if we don't show unnecessary detail. Our weapon construction should make sense, if only visually, but this is the only thing that matters in the end. Nobody's gonna disassemble it and check. Different manufacturing methods have different visual footprints on the final pieces. This sometimes translates into unintended shapes, textures, or details that we can use to enhance our piece's realism. In reality, the manufacturers usually try to hide or correct these imperfections and create an object as smooth as possible. For 3D pieces, the exact opposite is true. The more perfect a piece is, the more fake it looks. It might therefore be an advantage for us to recreate and even exaggerate these manufacturing imperfections with the goal of making our pieces more believable, but still trying to be subtle about it. They can enhance a good model, but they can't save a bad one by themselves. Some examples include parting lines from casting metal or plastic pieces using a two-parted mold inside which the material is injected and cooled down, resulting in a thin line where the mold parts are separated. Notice how plastic pieces are always freely conformed in molds, so manufacturers also take the chance to add any logos, markings, or warning messages they wish. We can also find parallel or concentric lines from the milling process of machined metal. These pieces are formed or finished by a milling machine, which is essentially a rotating head that removes material, resulting in these lines from each of the passes. The edges of these pieces are very sharp too, because of the precision of this manufacturing method. Stamping markings on metal with enough force displaces material and creates some small positive height around the stamped negative surface. This is starkly opposed to the more clean result of engravings, which leaves a much smaller footprint in the material. Next are the classic metal indentations to give structural strength to punched sheet metal. This is less of an imperfection and more of a necessity because of the characteristics of the material itself. Sheet metal is very flimsy, so these grooves are added to make conformed sheets stronger. Think of how a single sheet of cardboard is very easily deformed, but if we bend it, we can suddenly put a lot of weight on it without an issue.